Dear students, in the last class we discussed some basic factors of vector multiplication. There are two types of vector multiplication: scalar product of vectors and vector product of vectors, and their definitions. All those things we discussed in the last class. And we also discussed another property called derivative of a vector. The given vector is a function of a scalar, then rate of variation of that vector with respect to that scalar is called the derivative. In general, any vector A, if it is a function of the scalar, say t, in that case dA vector by dt represents the derivative of that vector. And there are some properties of the derivative of the addition, subtraction and vector multiplication if you apply the derivative property for addition, subtraction, multiplication, etc. See here, d by dt of a vector plus b vector, it's given by dA vector by dt plus db vector by dt. Similarly, d by dt of a minus b is dA by dt minus db by dt. And derivative of the dot product, a dot b, the dot product of the scalar product, we already discussed in the previous class. D by dt, the derivative of a vector dot b vector is defined as derivative of a dot b plus a dot derivative of b. It's also same as b dot derivative of a plus derivative of b dot a. These two are the same. Since the scalar product is a scalar product of vectors is a scalar, these two are equal. Now, derivative of the vector product, d by dt of a cross b, it's given by derivative of a cross b plus a cross derivative of b. This is not same as, see, this is not same as b cross derivative of a plus derivative of b cross a, not same. Those two are not same since it is a vector. One more property is derivative of a vector dot a vector. As per this rule, it is given by derivative of a dot a plus a vector dot derivative of a. These two are the same. Since it is a scalar product, these two are equal. Therefore, it can be taken as twice a vector dot derivative of a. So, these two are equal. So, it is nothing but twice a vector dot derivative of a with respect to t. And by definition, what is a dot a vector dot a vector? So, in general it is a vector dot b vector is ab cos theta. Similarly, this becomes a cos theta, angle theta 0 cos 0 1 becomes a square. A dot a becomes a square. So, derivative of a square is equal to this. And now here a is a scalar, it's a variable. So, if you derive it, it's not a vector but it's a scalar quantity, but it's a variable. It varies with time. The scalar quantity varies with time. So, if you differentiate, you get 2a dA by dt. A is a scalar, that's what magnitude of that vector A. Given by this, 2 gets cancelled, and from this we get the result a dA by dt is always equal to a vector dot dA vector by dt. This result is always true. In case of a vector dot a vector d by dt of a vector dot a vector, we get a dA by dt equal to this much. This is true for a vector which is a function of a scalar t. Suppose the vector a is of constant magnitude, modulus of a vector or simply a. If it is constant, its magnitude is constant. In that case, dA by dt equal to 0. You know this fact very well. If a is a constant, variation of a with respect to that variable t is 0. So that we get a dA by dt equal to 0. This term becomes 0. That means a vector dot derivative of a vector is equal to 0. See, when vector a is of constant magnitude, this result is true. Or this to happen, for this thing to happen, a should have constant magnitude. And one more thing. See, here, if a vector dot dA vector by dt equal to 0, suppose this is 0, dot product of these two 0. That means, see, and we are given a is of constant magnitude. This is possible only when a is of constant magnitude. So, a constant, so that now if this is equal to 0, in that case a dA by dt cos theta becomes 0. This is possible only when theta is 90 because this one becomes 0 only when cos theta is 0 because A cannot be 0. The magnitude of the vector is not 0 but it is constant but it is not 0. So then this equation to happen cos theta should be equal to 0. Cos theta 0 means theta is always 90. For theta 90 cos theta is 0. That implies theta 90 means angle between the vector A and d vector by dt. It is equal to 90 means A vector and d vector by dt are mutually perpendicular to each other. This is another result. So these are all true in case the vector A is of constant magnitude. When A is constant, this is true, and if this is true, then A vector dot A vector by dt or A vector and this are mutually perpendicular. These are some of the results based on the scalar product and derivative of scalar product and vector product of vectors. Now next topic is derivative of a vector of constant magnitude but changing direction. See here we have a vector A vector of constant magnitude but its direction changes with time. Direction changes means that particular vector is describing a circle. See here, consider a vector A represented by the line OP. OP, the line which represents the vector A. To start with, P coincides with M. P would be at this point M, so that theta 0. As time t increases, this A vector, nothing but OP, or the point tip of the vector OP, that is P describes a circle having theta varying between 0 and 2 pi. When it comes back to the same point here, the total angular displacement, it becomes 2 pi radian or 360 degree or 2 pi radian. So that's the meaning. The vector A is of constant magnitude but changing direction. Why magnitude constant? Because for this circular path, this OP, the radius of the circle, it remains constant everywhere. OP magnitude, length OP remains constant everywhere, but theta goes on changing, indicating that the vector A is having constant magnitude but changing direction. Consider one such vector of constant magnitude and changing direction. Let the vector A, it is changing with the direction theta. It's a function of theta. Now the magnitude is not changing. Now, this vector A represented by the line OP, it is in two-dimensional Cartesian coordinate system. It's a planar vector. A planar vector means a vector restricted to single plane. A vector restricted to a single plane is called a planar vector. Here we have a planar vector A represented by the line OP. It is in XY plane. So that the given vector A can be represented in terms of its components as A vector is A1 I cap plus A2 j cap. In XY plane, only two coordinates A1 and A2. A1, the component along x direction, A2, component along y, I cap, j cap are the unit vectors along x and y directions respectively. So this is how A vector is represented in terms of its components. Now, consider another vector perpendicular to this A vector. OP, the A vector perpendicular to OP means, see, this is the perpendicular vector represented by OQ. OQ, the perpendicular vector represented as A perpendicular vector. This is a symbol. A and a perpendicular mark and arrowhead. So OQ is a vector perpendicular to OP, nothing but the A vector. Let A1 dash, A2 dash be the components of A perpendicular vector along x and y directions respectively. So that A perpendicular vector, it can be represented in terms of its components as A perpendicular vector is minus A1 dash I cap plus A2 dash j cap. Minus A1 dash I cap plus A2 dash j cap. Why it is minus? Because the x component is in the negative x axis. A1 dash, the x component is in the negative x axis, that's why it is minus. So this is a representation of A perpendicular vector in terms of its components. Now let us find out a1, a2, a1 dash and a2 dash. What are the expressions for those components in terms of the magnitude of the vector A and that of a perpendicular vector? For that, first consider the triangle OPM. See here, a perpendicular is drawn from P on this x-axis. So this is x, this is y. Perpendicular from P on x-axis, this is PM. Similarly, perpendicular QN on x-axis. From the triangle OPM, a right angle triangle. In this right angle triangle, define cos theta. In this triangle, let us define cos theta. By definition, cos theta is adjacent side divided by hypotenuse. So here, cos theta is adjacent is OM, hypotenuse is OP. So OM by OP. But OM, what actually OM is? It is the x component of that A vector, nothing but A1. So it is A1 by A. From this we get A1 as A cos theta. The magnitude of the x component A1 is given by A cos theta. Similarly, in the same triangle, define sin theta. Same triangle, you define sin theta, opposite. It is PM by the hypotenuse OP. Opposite by hypotenuse, PM by OP. What is PM? PM is nothing but the y component. Y component of this vector A, nothing but A2. So that A2 by A. From this we get A2 as A sin theta. This we have the expressions for A1 and A2 in terms of A and the direction theta. Now substitute these values in the expression for A. So you get A vector as A vector is equal to A cos theta I cap plus A sin theta j cap. The expression for A vector. Let the equation be 1. Now similar way, let us find out the expression for A perpendicular vector in terms of A and the direction theta. For that, consider the triangle OQN. Here, this angle is theta. If you find the geometry, so this is 90, this is 90, then the alternate angles, these two are equal. Here, these two alternate angles, they are equal. If you consider all those things, you get this angle as theta. So that in this right angle triangle, define sin theta. In this triangle, define sin theta. Sin theta is defined as opposite ON by OQ. What is ON? Nothing but x component of this A perpendicular vector. X component is A1 dash. So it is A1 dash by A, or from this we get A1 dash as A sin theta. Similarly, in the same triangle, define cos theta. Cos theta is adjacent. It is QN divided by OQ. QN is nothing but y component A2 dash divided by A. So that from that we get A2 dash as A cos theta. Substitute. We get the expression for A perpendicular vector as minus A sin theta I cap plus A cos theta j cap. Thus, we have now the expressions for A1 vector and A perpendicular vector in terms of A and theta. Now, consider equation 1. This here A vector of constant magnitude but changing direction, indicating that A is the function of theta. It varies with its variation in direction only, so it is not a function of t. So direction, it is a function of theta. So that find the derivative of the expression 1. That means consider dA vector by d theta. Differentiate A with respect to theta. It is a function of theta now, not t. It depends on theta. So that dA vector by d theta. Let us consider derivative of this A vector with respect to theta, the variable theta. So dA vector by d theta. If you differentiate with respect to theta, you get dA vector by d theta is equal to A. Differentiation of cos theta is minus sin theta I cap plus A cos theta j cap. You get dA vector by d theta as minus A sin theta I cap plus A cos theta j cap. And look at this equation on the right hand side. This is same as expression for A perpendicular. If you compare these two are same, indicating that dA vector by d theta is A perpendicular vector. When we consider the derivative of the A vector with respect to theta, then we get the perpendicular vector. So dA vector by d theta equal to A perpendicular. This is one result. Similarly, now let us derive equation 2. That is, let us find out derivative of A perpendicular vector with respect to theta. What do you get? Differentiate with respect to theta. That is, dA perpendicular vector by d theta, left hand side, is equal to, here minus sign already there, differentiate sin theta, you get cos theta. So this is minus A cos theta I cap plus A differentiation of cos theta is minus sin theta. So you get minus A sin theta j cap. The equation becomes even. Minus A cos theta I cap minus A sin theta j cap. Minus sign common, keeping outside, you get inside the bracket, inside brackets, A cos theta I cap plus A sin theta j cap. But what is A cos theta I cap plus A sin theta j cap? It's nothing but equation 1. A cos theta I cap plus A sin theta j cap. The term inside the bracket is nothing but equation 1. It is nothing but, what is it? A vector. So that dA perpendicular vector by d theta, what do we get? Minus A vector. This is another result. For all vectors of constant magnitude, varying direction, these two results are true. Whenever we find the derivative of one vector with respect to the direction, you get the perpendicular vector. Derivative of the perpendicular vector is always equal to minus of the given vector. These are the two results. These are nothing but derivative of a vector of constant magnitude but changing direction. This very important derivations, these expressions, you have to remember these things. So if these two are true, then these two results are true for the unit vectors also. These two results are true for any vectors, means they are true for unit vectors also. Say any vector A, any vector in general can be written as the product of the magnitude and the unit vector denoted as A cap. The given vector A, it can be written as product of its magnitude and the unit vector denoted as A cap. Similarly, you can write A perpendicular vector as A, magnitude same, see both the vectors, these two are in the same magnitude, but the unit vector is different, direction different means the unit vector is A perpendicular cap. Then dA vector by d theta gives A perpendicular vector, dA perpendicular vector by d theta gives minus A vector. In a similar manner, dA cap by d theta gives A perpendicular cap, dA perpendicular cap by d theta gives minus A cap. These are the results that are true for unit vectors. Very important. dA cap by d theta, the variable is theta, remember, not t. dA cap by d theta, variation with respect to direct change in direction, is A perpendicular cap, and dA perpendicular cap by d theta is equal to minus A cap, and these are very important results. And this is about derivative of a vector of constant magnitude but changing direction. And these things I am now let us consider the derivative of the position vector of a particle which is moving in space. Suppose there is a particle which is moving in space. In space means a particle is represented by three coordinates. Space, a three-dimensional Cartesian coordinate system. So a particle moving in space has got three coordinates. Consider a particle moving in space. A particle is P. X, Y, Z are the coordinates of this moving particle. So the position of the particle at any instant t, position of the particle at any instant t is given by the coordinates x, y and z. The particle is moving in space. So there are three coordinates, x, y, z are the position coordinates of that particle. Now the line joining the origin to the particle OP is called as position vector of the particle, denoted as R. the line joining OP. It specifies the position of the particle in space at any instant, called the position vector, denoted as R. And this position vector R, it can be represented in terms of its position coordinates as x I cap plus y j cap plus z k cap. Representation of the position vector of the particle, which is the function of time t. Position vector is a function of time t. It is varying with the time. As time changes, the position of the particle also changes. The particle will be, while moving, will be in different positions at different time instants. So position vector is given by this. Now, the magnitude of this position vector, mod r, nothing but r is equal to square root of, we had seen in the last class, x squared plus y squared plus z squared. This is the magnitude of the position vector of the particle. As position vector is the function of time t, the coordinates x, y, z are also the functions of t. They are also vary with time. As r changes with time, x, y, z, they are also changing with time. Then, the rate of variation of the position of the particle. Rate of variation of the position of the particle. Nothing but the derivative of the vector r. Rate of variation in the position of the particle, dr vector by dt. It is nothing but d by dt of x I cap plus y j cap plus z k cap. As I told, x, y, z are also functions of t. So that we get dx by dt I cap plus dy by dt j cap plus dz by dt k cap. The rate of variation of position of the particle, it is defined as, it is nothing but the velocity, the instantaneous velocity of the particle. The rate of change of position is called the velocity, or the instantaneous velocity is given by this. Or the instantaneous velocity of the particle is given by dx by dt. The first derivative of x with respect to t denoted by as x dot. So x dot I cap plus dy by dt denoted as y dot j cap plus dz by dt z dot k cap. The first derivative always represented by the dot at the top. Thus, the instantaneous velocity of the particle, rate of change of position, nothing but velocity given by this. What about the magnitude of velocity? Mod v. Mod v vector, or simply v, given by square root of x dot square plus y dot square plus z dot square. This is the magnitude. Next is, suppose, see, here velocity also changing with time. Velocity is also changing with time. Velocity changes with time means the particle is called acceleration. We define acceleration of a particle as the rate of change of its velocity. Nothing but dv vector by dt. A is the instantaneous acceleration of the particle. Rate of variation of velocity, dv vector by dt. Or A vector is given by d by dt of, what's our v vector? V vector is given by this. X dot I cap plus y dot j cap plus z dot k cap. X, y, z are the functions of t. X dot, y dot, z dot are also the functions of t. Therefore, A is given by, acceleration is given by dx dot by dt I cap plus dy dot by dt j cap plus dz dot by dt k cap. Or now, the derivative of x dot, it is denoted as x double dot I cap plus y double dot j cap plus z double dot k cap. This is the expression for instantaneous acceleration or acceleration at any instant. Acceleration of the particle at any instant is given by this expression, and mod A or magnitude is given by root of x double dot square plus y double dot square plus z double dot square. And these are the derivative of the position vector when a particle is in motion in space. Whenever a particle is in motion in space, the derivative of the position vector gives the velocity vector. derivative of the velocity vector gives us the acceleration. This is about the derivatives. With this, I stop here. Let us continue the class with some other topic. Thank you.